All right. Hi, everyone. Welcome to the AOS Department Seminar. Today's speaker is Jacob Beitlich, who is a lead forecaster for the National Weather Service in the Twin Cities, Minnesota office. He was a member of the Central Region Tornado Warning Improvement Project and helped develop training material for Quasi-Linear Convective Systems. He earned his master's degree from the UW-Madison AOS department in December of 2009, and he is very excited to be with all of you today. So with that, I'll turn the mic over to Jacob.
All right, thank you, Gerald, and thank you for that introduction. Thank you all for your time and attendance. As Gerald alluded to, I'm very honored to be here, and I'm looking forward to this. So with that, let's get started. The title of the talk is an overview of the Quasi-Linear Convective System, or QLCS, training curriculum, and the 3 ingredients method. So that's courtesy of the Central Region Tornado Warning Improvement Project team. This team was tasked to connect peer-reviewed research to operational meteorology, in particular warning forecasts. So the team developed about 7 hours of training, and I tried to take that and to condense it down into 30 minutes worth of material while still giving it due diligence. So there's a few key terms and concepts that we'll see repeated through this presentation. They're listed on the left. We have QLCS, Mesovortex, UDCZ, 3 ingredients method, and Shear cold pool balance regimes. So a quasi-linear convective system is a line of storms that often contains mesovortices, which are areas of enhanced circulation and can produce tornadoes. The loop that you're seeing on your screen right now is from September of 2018, September 20th to be exact. And this is a 1-hour radar loop. So in 1 hour, these storms are covering about 3 counties across Minnesota. And this was a pretty remarkable event, and you can see what we have is a linear appearance on reflectivity on the left. But if you look to the right in the velocity, you'll see that we have embedded circulations, and those are the mesovortices, the mesovortices that we'll talk about that can produce tornadoes. This was a very proficient tornado producer. It produced over 24 tornadoes over the course of a few hours. So a really dynamic event. So the motivation behind this presentation and the whole team in general can be summed up nicely from one event back in mid-June of 2014. So the radar image in front of you is from 20Z on June 16th. And what I'm going to do is loop through about 10 hours worth of composite reflectivity, and you can watch these storms do what we call grow upscale into a line of thunderstorms, or a QLCS. So by the time it gets to Wisconsin, you can see we have a well-defined line of storms and another one forming in Iowa. So I want to break this down into 2 parts. Well, first of all, that event had 29 tornadoes, and of those 29, 19 were unwarned. So that's why I said there's plenty of motivation with that event. I'm going to break it down and to look at the first part, which was supercell tornadoes. You can see the composite reflectivity. You have your discrete cells, your supercells across northeast Nebraska into northern Iowa. And during this time, there were 6 tornadoes. And of those 6, only one of them didn't have a warning. So we had a probability of detection, that's what POD stands for, of 83%. And the average lead time was over 15 minutes. So those are stats that we strive for as warning forecasters in the National Weather Service, to detect the tornadoes and give ample lead time for people to take cover. So this was a pretty remarkable event. This was the Pilger, Nebraska tornado. And while this was ongoing, there were 2 stovepipe tornadoes, high-end EF3, EF4 tornadoes ongoing at the same time. So a pretty remarkable event in the first part. Now we'll go to the second part, and that is QLCS tornadoes. So I have thumbnails of the 8 radar timestamps right there. And there were 23 tornadoes during this second part. And of them, 18 were unwarned. So that's only a probability of detection of 22%. And the lead time was less than half of what we saw with those supercell tornadoes. So this is one area that the tornado warning improvement project team really wanted to target, were these QLCS events, because they're challenging. So a few of you may remember that June 17th, right around midnight. If you lived in Verona, that's when you had a tornado move through. Again, unwarned, this was an EF3 tornado, and there's a picture of some of the damage from Verona, Wisconsin. So just down the road from the AOS building. So now we're going to talk, we kind of summarize the motivation. Now we're going to go back and look at sort of the baseline understanding of these events and see how we can apply that later on into some radar features and radar signatures. So the conceptual model for QLCS tornado. I have a schematic from Atkins and Laurent on 2009 on the right. And we'll talk about the process of these mesovortices. Descending parcels, usually the rear inflow jet of the storm, acquire horizontal streamwise vorticity. These parcels are tilted and then stretched as they encounter the updraft region. And vertical vorticity rapidly increases as parcels are stretched in the updraft. So if you draw your attention to the schematic in the upper right, I'm going to highlight that area of how a cyclonic mesovortex develops. The parcels come down, they acquire that streamwise vorticity, and they're stretched in the updraft. So what do these look like? Typically, they're resolvable by radar at around 3,000 to 5,000 feet above ground level. They evolve rapidly and can grow upwards. Waiting for mature mesovortices to form before issuing tornado warnings offers little to no lead time. The tornado's probably already on the ground. But this last bullet's pretty important. These mesovortices always develop and remain tethered to the updraft, downdraft convergence zone. So always, that is a very strong word, especially in the field of meteorology. I think back to my days of 452, the geostrophic wind is always non-divergent. And John, you can correct me at the end of this if I'm wrong on that, but always, 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 always. If you can hold on to statements like that, they'll get you far. So the mesovortices always remain tethered to this UDCZ. That was one of the key terms. So I'm going to highlight this on the radar images. And so what we have is storm relative motion on the right, and then reflectivity on the left. And I've highlighted the UDCZ, that updraft, downdraft convergence zone, by the dashed line. So we'll just move through this slowly, and you can see the mesovortices, those couplets on the velocity image, the storm relative motion image on the right, remain tethered to this updraft, downdraft convergence zone. So it's very easy to identify that on the storm relative motion part of the image on the right. But if you look at the reflectivity, it's not quite so easy. Sometimes you're right on the leading edge of the reflectivity, sometimes you wrap behind it, and that's going to take us to the next part of this presentation. So the UDCZ, what is it? The updraft, downdraft convergence zone is the leading edge, is where the leading edge of a thunderstorm cold pool meets the updraft. So we'll look at a few schematics here. This is one that you already saw. And that UDCZ is indicated by that little black line in this diagram. Look at another schematic. Here's a cross section and then a bird's eye view of a thunderstorm. So you can see the red arrows representing the updraft, the blue arrows representing the downdraft, and that UDCZ is that little frontal boundary indication of the leading edge of the cold pool. It's where that updraft meets the cold pool. So why is that important? The UDCZ is critical in determining where shear cold pool balance, in determining shear cold pool balance regimes with QLCS. So that's a mouthful, but we'll go through that over the next few slides. These mesovortices form along the UDCZ. and they remain tethered to it. So if you can focus on the UDCZ, that updraft, downdraft convergence zone, it eliminates a lot of area where mesovortices and tornadoes are not a concern. So you can really find areas of the storm to hone in on if you're a warning forecaster, and then other areas of the storm where you can be less concerned. So how do we find the UDCZ? And we're looking at storm relative motion and velocity here. Always start with the half-degree storm relative motion and velocity. You can use spectrum width and reflectivity as aids. Step back and forth using a few higher tilts like 0.9 or 1.3 degrees if necessary. And the great thing about this is it can be determined at pretty far distances from the RDA, from the radar. So I got my little radar icon in there, and I have those yellow lines showing the different distances. So I can find the UDCZ, the updraft, downdraft convergence zone, on my velocity products. So we're going to go through a few examples. This presentation is full of examples. So what I have are 4-panel radar images, and these are from the same time and the same elevation, and they're labeled accordingly. The upper left is your reflectivity. The upper right is the storm relative motion or storm relative velocity. The lower right is your velocity, and then the lower left is your spectrum width. So I'm just going to go through and plot the UDCZ on all 4 of my radar panels. So then I'll zoom in and highlight where those mesovortices are, and lo and behold, they're right on that UDCZ. So here's another example, a different example, same setup. And I'll give you a minute to look at it, see if you can identify the UDCZ. Again, you want to focus on the velocity products, not so much the radar product, but we'll look at the radar later, and that will tell us a little bit more about the storm and potential for mesovortices. So here I am drawing it on, and you'll see these show up. All right, so now the next one. Again, I'll give you a minute here, or a few seconds, I should say. So look at the velocity panels, either the SRM or the true velocity on the right-hand side. And we'll see the UDCZ, indicated by the white dashed line. All right, one more. This is a fun one. So pretty evident. It probably jumps out at you there, especially where you have your outbound velocities, your red colors in the SRM, and your inbound velocities, your green in the SRM in the top right there. So I'll go ahead and plot those on. And again, there are your mesovortices that are right on the UDCZ. So let's focus in on this middle mesovortex. So what I did is I drew a white box around that, and I want you to pretend that you are on the bottom of that box, the southern side, facing to the north. So you're going to look right into that storm, into the UDCZ. And this is what that would look like. So I have the thumbnail in the upper left there of where that box is, and you're standing right where the word south is in those little thumbnails, and you're looking due north, and you can see the updraft, downdraft convergence zone really apparent on storm relative motion on the right, and not so much on the reflectivity on the left. And I'm going to plot this at different elevations just to give you some indication that it has depth, which is great because as we're looking at the radar, when we're close to the radar, we're looking low in the storm, but as we get farther away, we're higher up into the storm. So if we can identify features in a storm that are at great distances away from the radar, that will help us in detecting severe weather farther away from the radar, which is a challenge. So a big part of this training was the QLCS Mesovortex warning system, and the 3 ingredients method was a part of that system. So I want to focus on the 3 ingredients method for the remainder of this talk. So we use the 3 ingredients method to anticipate where mesovortex genesis is likely over the next 30 to 45 minutes. What we're trying to do is anticipate where these mesovortices are going to form in the future. We don't want to wait for that couplet to show up on our velocity, because remember, that offers little to no lead time. So we're going to try to identify features and use this near storm environment, use some radar cues to predict where are these mesovortices going to develop in the future. So ingredient 1 of the 3 ingredients method is the system cold pool and ambient low-level shear are balanced or slightly shear dominant. So I have the other 2 ingredients on here as well, and I'll go through those in more detail. That's why they're grayed out. So ingredient 2 is a 0 to 3 kilometer line normal bulk shear magnitude is at least 30 knots. And ingredient 3 is the rear inflow jet or enhanced outflow causes a surge or bow within a QLCS. But going back to ingredient 1, system cold pool and ambient low-level shear are balanced or slightly shear dominant. If we have enough time, I can go through a few extra slides that explain this in more detail from a conceptual standpoint. So we're going to go straight to the examples. We're going to do what we just did. We're going to find the UDCZ. So I'm going to draw that in now, similar to the way we did it before. And then we're going to compare that to reflectivity. So there's a reason why we have reflectivity up there, even though it's not great at identifying where the UDCZ is. We can get some information as to where the UDCZ is located relative to the reflectivity. So shear dominant, what does it mean to be shear dominant? That has the UDCZ within or even behind the convective towers. So basically within the higher reflectivity values. So I'm going to label that for you, and that is the white area of the UDCZ, the white dashed line. That is the region of the storm where the UDCZ, the shear cold pool balance is shear dominant. So shear is dominating in that part of the storm. Balanced has the UDCZ on the immediate front edge of the convective towers. So I'm going to highlight that with that black label. So the black dashed part of this line is where the UDCZ is balanced. The shear and the cold pool are imbalanced. And then finally, we have the cold pool dominant part of the UDCZ. That has the UDCZ out ahead of the convective towers. So you can think of the gas front racing out ahead of the convection. So that part is slightly cold pool dominant. And if you think about it, if you had no shear, you just dropped a cold pool, it's going to race out ahead of the storm, right? It happens all the time in Florida. So that's an example of a cold pool dominant part of the storm. So we're going to go through a few more examples, find the UDCZ, and compare it to reflectivity. And so that's how we're going to identify ingredient 1 of the 3 ingredients method. So looking at the UDCZ and then comparing it to the reflectivity in the upper left, where it is behind the updraft towers, slightly shear dominant, where it is where it's right on the leading edge, it's balanced, and where it's ahead of convection, it's slightly cold pool dominant. So I zoomed in on that area of the storm. So another example here, we already saw this one, but we're going to now look at it relative to the shear cold pool balance regime. So we find the UDCZ. And that top part is right on the leading edge of the convection. That's the balance part. And that lower part that's indicated by the yellow, that is a slightly cold pool and a strongly cold pool dominant part of the storm. So what's great about this is where you have a cold pool dominant part, that's a very unfavorable region for mesovortices to develop. So we can eliminate a large part of this line of convection with regards to mesovortex potential, and we can only focus on that balanced area. So that is where we want to hone in on if I'm a warning forecaster of the potential for mesovortices and tornadoes to develop. All right, we'll do another example. I'll plot this. And if you've been paying attention to the dates, a lot of these are in the late fall or early spring, some even in winter down south. So these are your dynamically driven, synoptically forced severe weather events. It's not your dry line or middle of summer peak heating type of event. It's later on where you got dynamics to work. So the top part is slightly shear dominant, and the whole rest of this line is balanced. So that was ingredient 1. Identify the UDCZ and then determine if it is shear dominant, balanced, or cold pool dominant. That's ingredient 1. Ingredient 2 of the 3 ingredients method is the 0 to 3 kilometer line normal bulk shear magnitude is greater than or equal to 30 knots. So this is a fun little exercise. This is one of my favorite slides. So what we're going to do is we're going to find the UDCZ and compare it to reflectivity, and then focus on the areas of the UDCZ where the values of the 0 to 3 kilometer line normal bulk shear are near or above 30 knots. So what I have is just a few examples of UDCZ. That's my conceptual model, my white dashed line there. And then I have some wind vectors that represent the 0 to 3 kilometer bulk shear. So the top one is 30 knots. But if you go to that middle one, it's 35 knots. So if you dig deep into your days of trigonometry, I think it is, or whatever it is, where you're figuring out the angles using the sine and the cosine, you can see that you can rotate that UDCZ about 30 degrees, and you'll still have a component that is at least 30 knots. So if we even get stronger shear, we can rotate that shear vector, meaning that doesn't have to be orthogonal to our UDCZ. It can be just a component of it that would be enough to have that 30 knots. So that's the idea behind the line normal component of the 30 knot of the 0 to 3 kilometer bulk shear is at least 30 knots. So that's the idea behind it. So let's just for fun plot out a real UDCZ, and let's just throw on some shear vectors from the near storm environment of an arbitrary severe weather event. So let's look at the shear vectors ahead of the UDCZ. So kind of to the, as you're looking at it, to the right. So the storm is moving from west to east, from left to right. So we want to look at the environment that the storm is moving into. So if you look at this, we have near or above 30 knots of 0 to 3 kilometer line normal bulk shear within this pink oval. That's where you have a pretty large component of that shear vector normal to the UDCZ, at least 30 knots. But if you look down to the south and southwest a little, you have less than that. Your shear vector is almost parallel to your UDCZ. So you have a much smaller component of that shear vector that's going to be acting normal to the UDCZ. So then I will just throw up a storm and look at that. Look where you have your convective towers relative to the UDCZ. It is balanced. And not coincidentally, it is balanced where you have that 30 knot component of the 0 to 3 kilometer line, 0 to 3 kilometer shear perpendicular to the UDCZ. So you have at least 30 knots of the 0 to 3 kilometer shear normal to the UDCZ. But if you look further to the south where it's cold pool dominant, again, not by coincidence, you don't have that much contribution of that 0 to 3 kilometer shear to the UDCZ. It's mainly parallel to it. So this is a really powerful slide showing how that 0 to 3 kilometer shear is important especially regarding the UDCZ. So this pink area is a favorable region for mesovortices. Meanwhile, that area in the blue oval down to the south, that's an unfavorable region. You're cold pool dominant, so you don't have that first ingredient, and you don't have the 0 to 3 kilometer shear component either. So you're missing 2 ingredients right off the bat. So let's jump to that third ingredient. That is the rear inflow jet, or the RIJ, or enhanced outflow causes a surge or a bow within a QLCS. So you want to be able to see kind of this line surging ahead a little bit or bowing out. If you see that, that is the third ingredient. So why are these important? Bows and surges often represent an area of descending parcels. So you think back to that schematic, descending parcels, that's an important part of where you get that vorticity. So increased convergence may locally enhance upward vertical motion and aid in that stretching potential. And cyclonic mesovortices typically develop just north of a and then you have your green area. Yeah.
We lost you just for a second. You were gone for about maybe 30 seconds.
Okay. I thought you jumped off.
Yeah, that was weird. Anyways.
Okay. I'll just start with the schematic up here. So the bow and the surge, that's where you can get potential for that stretching to take place. You get your descending parcels, and then you might be able to lift that up. So I'll draw your attention to that upper left bird's eye view, or excuse me, upper right bird's eye view, and the descending rear inflow jet I've highlighted with that blue shading, and then these local surges where you have that higher vorticity. Those are indicated by the green, and that lines up, if you can imagine, that cyclonic mesovortex that's in the schematics below it. So example of a surge in a bow. We use the mesovortex conceptual model to understand and anticipate these processes while interrogating the radar. So we want to try to anticipate what is going on. So I'm going to give you the first 3 images of a storm from the velocity, half degree. So these are taken 5 minutes apart. And in this part, you have descending rear inflow jet advances toward the leading edge of a gust front. So this first radar image, mind you, is at 428Z. Now we'll jump forward, again, 3 more images in 5-minute increments. And so what you see now is small surges developing along with notable increase in storm inflow. So that the red value, the red colors that you're seeing are increasing. So there's actually getting more air ingested into the storm, more inflow, more updraft. You can see that RIJ descending and pushing right toward your UDCZ. I don't have it labeled there, but it's where the red and the greens are coming together. So finally, at 459Z, we have mesovortices that have developed, and one of them is producing an EF1 tornado. So this whole idea is if we can anticipate where these mesovortices are going to develop in the future, using the 3 ingredients method, we can issue tornado warnings before the mesovortices even develop and before the tornadoes develop. So if you look back to this radar image, 30 minutes prior, you could have said, all right, I'm starting to see a rear inflow jet descend. Do I have a UDCZ that is balanced? And in this case, you did. So ingredient 1. Do you have at least 30 knots of 0 to 3 kilometer shear? Yes, you do. Ingredient 2 is there. Now you're starting to see that bow or that surge. You're thinking to yourself, okay, 3 ingredients are in place. I got to be ready and anticipate some mesovortices developing. So we'll just go through this one more time. The mesovortex genesis and intensification are favored where the following criteria are co-located within a QLCS. The system cold pool and ambient low-level shear are balanced or slightly shear dominant. The 0 to 3 kilometer line normal bulk shear is at least 30 knots. And the rear inflow jet or enhanced outflow causes a surge or bow within a QLCS. So we're going to put this into practice now, and we're going to look at an event. This is from February 14th of 2017, just in southern Texas, okay? That's where we are to orient yourself. So I have the 3 ingredients there to remind you for reference. Here's a look at the reflectivity from 14Z. And I'm going to show some shear vectors for you as well. So I've faded that out a little bit, but you can see you have quite a bit of shear, 45 knots or so. But look how it's oriented. So just pay attention to how that orientation from the southwest could affect the storm. So if we have a storm like that, a UDCZ like that, that's good. But we can rotate it 40 degrees because we do have such high values of the 0 to 3 kilometer shear. So it doesn't have to be truly normal to get the full 30 knots. So here's a look at 1401Z at the reflectivity and the velocity and the spectrum width. So I'm going to draw these, and you can see for the most part this is a balanced shear cold pool balance regime. So we have ingredient 1. We're going to look for where is ingredient 2 in place. All right, that's where ingredient 1 is in place, the cyan line. Where is ingredient 2? That's that orange line right here. So an area where I can see kind of a northwest to southeast orientation of the line would be ideal, but anything close to that is going to. And where is a surge or a bow? We have a couple of those, three to be exact, showing up. So these areas highlighted by the white circle, those are your favored regions for mesovortex genesis. If you're the warning forecaster, the radiator, that's where you're dialed in. And it looks like we do start to have maybe some indication of some cyclonic rotation. I don't know if I would call that a true mesovortex, but there is some indication there. We'll jump forward 8 minutes, all right? We'll do the same thing. Excuse me. I'll let this play through. And so we're basically balanced the entire way, but now we do have that small area that is slightly shear dominant. We still have that slightly cold pool dominant area to the south. So ingredient 1 is met across most of the line. There are a few more areas where we have at least 30 knots of 0 to 3 kilometer shear. And then we have surges and bows. So it's getting a little more complicated. This is getting to be a pretty tricky event. Remember, this is at in the morning of February 14th. So not exactly when you're thinking peak climatology for tornadoes, right? So we have 5 areas of favored regions for mesovortex genesis. And I've highlighted a few of them so you can see them a little bit closer. All right, now we'll jump ahead about 15 minutes. Again, we're going to draw the UDCZ, label it according to the reflectivity where we're balanced, slightly shear dominant, balanced, and then slightly cold pool dominant to the south. So again, ingredient 1, that's in place. That's that cyan line all the way along there. We're balanced or slightly shear dominant. We have several areas where we have at least 30 knots of line normal shear. And we have several areas now where we have a surge or a bow. So these are the favored regions for mesovortex genesis. And I think I have the, yep, there we go. So we can zoom in, and now we start to see what is definitely a couplet, meaning an area where you have gate-to-gate shear, where your inbounds and your outbounds are right next to each other on the storm relative motion. So probably a tornado ongoing or else going to occur shortly with that middle mesovortex that's just to the west of your radar. We'll go through 12 more minutes. We'll plot the UDCZ again. We have quite a few favored regions for mesovortex genesis. I'll zoom in on those for you so you can take a look. And this one's tricky because the line is moving right along toward the radar. So you looking at the SRM, you have different values relative to the storm in different parts of the storm. So pretty challenging event that I'm showing you here. Then finally, the last one at 1459. So we'll draw in the UDCZ. You can see it's changed a little bit. It was all balanced to begin with, but now as we moved ahead 1 hour, there's a few areas now that are slightly shear dominant. So again, several regions for that are favorable for mesovortex genesis. And then we'll zoom in and look at the specific stronger mesovortices, especially that one that's just to the northwest of the radar. So what happened from that event? There were 7 tornadoes, a lot of wind damage. These mesovortices don't always produce tornadoes, but a lot of the times they do produce wind damage. One tornado was EF2, another one was EF1, and the remaining were EF0. So I have a couple more slides, and you saw from this last example that there's a lot of areas of the storm. There can be where you have favored regions for mesovortex genesis. So to try to reduce our false alarm, meaning we don't want to issue a tornado warning when there is not a tornado, we looked at radar features that are confidence builders. We call them confidence builders. So if you see more of these, that tells you that there's a better chance of tornado genesis. Not just mesovortex development, that's the 3 ingredients method. Now, how do we go from mesovortices to tornadoes? That's where these are. And these are more so just radar features, but I'll go through them. A descending rear inflow jet or reflectivity drop. So if you look there, the top one is from 131Z, that's the top row. And then if you go 5 minutes later, you can see how your reflectivity has dropped. If you see that, your lower reflectivity values, that indicates that you have a rear inflow jet descending. You're evaporating those hydrometeors behind that line of convection. So you have descending parcels. Remember, that's that first ingredient of the 3 ingredients method. An enhanced surge, that's another one. So if you see an actual bowing out developing, so not just a concave line of storms, but you actually see that surging out. That's another indicator that can give you the confidence to issue a tornado warning. So I'll go back and you can see that surge out, especially in the reflectivity. A line break. So a line break actually is another indicator of descending parcels. So if you look at that, there's a break in the convection. And then you do have a small area where you had a tornado ongoing with that. So really subtle feature, but something that we can detect on radar. This is a really good one. It's the UDCZ entry or inflection point. So I talked a little bit about that earlier. What that is, it's where you go from maybe a balanced to a slightly shear dominant part of the storm, where you make that inflection point, where you kind of go from being ahead of the convective towers to behind it. That's a really favorable region. We call that a UDCZ entry inflection point. That's what that is. So I'll zoom in on it a little bit more, and it's where you go from being right on the leading edge of those convective towers to behind it, where that arrow is pointing. So that is your entry point or your inflection point. A paired front rear inflow notch. So if you have that rear inflow notch and then maybe a one on the leading edge, that indicates a favorable setup for vorticity. So that could be another confidence builder for having a tornado develop. A boundary ingestion. So if you have a boundary laid out, we know those are sources of vorticity. So if you have a QLCS or a line of storms that's moving right along a boundary, odds are that you're going to have tornadoes along that. And I've indicated a couple of them there with that white arrow, those white arrows. A front reflectivity nub. Again, this is a really subtle feature, but it indicates that you have an updraft tower. So you have the potential for that stretching of vorticity in the mesovortex to become tornadic. So I've highlighted those with the little spotlights there. Pretty subtle features. Contracting bookend vortex. So you don't need the 3 ingredients for this one, but when you have a mature QLCS and you have that contracting bookend vortex, there's a lot of vorticity there. So if you see that contraction, that can tell you that, all right, I have a pretty good potential for these mesovortex tornadoes. Finally, a tight, strong mesovortex, that's self-explanatory, but look where that is relative to the reflectivity. So if you're looking at reflectivity, you're not going to find this, but if you're looking at the velocity products, the storm relative motion, you will. And so this shows that a lot of these QLCS tornadoes end up being rain wrapped, so they're very difficult to see and anticipate that they're coming just by looking at them. And then finally, tornadic debris signature. So we're able to detect non-meteorological echoes on the correlation coefficient, which is the CC in the lower left. And you can see that right there that it lines up with the couplet and the velocity in the upper right. So if you see, so these 10 radar signatures identify an increasing likelihood for tornadic development in a QLCS. If we see these features, we go from thinking, okay, this could produce mesovortices to this will probably produce tornadoes. Nudgers, these are just 4 more that aren't quite as highly weighted. And I'll just buzz through these quickly. The first one's a reflectivity tag. So if you see some reflectivity out ahead of your QLCS kind of lifting to the north, that's one that gives you a little bit of confidence, but not quite as much. So we call it a nudger. 0 to 3 kilometer ML cape. So if you have instability in the near storm environment ahead of this line, that makes us think that these storms can have a better chance of producing stronger updrafts and stretching that vorticity. A cell merger or a reflectivity spike, just another indication that you have stronger updraft when you have your reflectivity get a little bit stronger, shall I say, higher in return. And then lastly, this is another example of that where the previous scan is on the top, current scan's on the bottom, and you can see the reflectivity has intensified over that time. And then lastly, a history of tornadoes. So if you have a storm that has been producing these tornadoes, that can give you confidence to continue a warning if you're on the fence downstream. So that was a ton of peer-reviewed literature and case studies condensed into 7 hours, condensed into about 45 minutes. So thank you for your time and for your attention. And I'll toss it over to Gerald to see if there's any questions.
Yeah, if anyone has any questions, you can unmute yourself or type it in the chat box. Go ahead, John.
Yeah, Jake, fantastic presentation. Extraordinary, well illustrated, I think filled with really interesting information, and I really like the more than the tip of the hat to the synoptic scale on the whole thing too, which is great. I had one question that occurred through the middle of it. Are there times where the 0 to 3 kilometer shear and the surges are not coincident? There are places where it looks like the surges might be kind of not in the same place as the 0 to 3 kilometer shear, but those almost seem like overlapping characteristics of your or ingredients of your 3 ingredients, but not exactly. Can you comment on that?
I can try, John, and thank you. So that might be a limitation of the modeling and or the resolution of the radar. Some of these cases go back to before we had high resolution models. So the near storm environment that we're getting that 0 to 3 kilometer shear information off is a 40 kilometer grid. It's only updated once per hour. And I think a lot of the times these storms modify their own environment. And the 0 to 3 kilometer shear just doesn't catch up. And the reason I'll say that is we have a person here at our office that does do some higher resolution modeling. And I'm not saying it's right, but the values that you get where you see these mesovortices develop are much higher, like almost orders of magnitude than you'll see in a 40 kilometer grid. So I'm going to open that to you guys. I know you have some really fantastic modelers at the university, and I think it would be really cool to see kind of a reanalysis or a modeling of these types of setups. I mean, it's not the supercells, but man, there is a lot going on here, and I think it'd be really interesting. So I hope that answered your question.
It does, and it spawns a short follow-up if I could. I think those rear inflow downdraft regions that spawn the surges, and then on the north side of the surges, or on the I guess it is north side of the surges, where you have your risk increased. I wonder if those are mesoscale regions of enhanced convergence, so that there's an example of how the storm gets modified by some of its own internal dynamics. That if you create a local convergence maximum on an already vortex-rich strip, you're going to certainly spin something up right there, and that's going to be a sort of a dynamical interaction.
I think so. And I mean, you got my mind racing now. Like that rear inflow jet has a thermodynamic component to it, where you're evaporating the hydrometeors and you're generating that cold air that rushes down to the front. But then as soon as you disturb that balance, for lack of better words, in the storm, all of a sudden you have a dynamic response too. And I think sometimes they feed back on each other, and that's where you can get, if I can go back to my second slide here, an event that produced 24 tornadoes. We surveyed this with drones and high resolution satellite imagery. I mean, there were mesovortices everywhere. So it's fascinating when the ingredients come together. Boy, the atmosphere can really produce some fireworks.
Thanks, Jake. That was great.
All right.
It looks like Ian has a question.
Yeah, hi Jake. Thank you very much for the talk. Very interesting. My question kind of goes off what I think John was just getting to with his follow-up there, and goes off of the example that you gave us with where the shear was actually seemingly roughly more parallel to the line than it was normal. And my question, I guess, is sort of the rear inflow jet the big decision maker there, where when it causes a surge to go forward on the northern side of the bow, that's where you end up increasing your line normal bulk shear. And I'm correct me if I'm wrong, or if you already touched on that, but that's kind of what I'm gathering from that.
It was this example, right? Is this what you were talking about?
I'm thinking of the example in Texas where, it seemed like right as the bow started, I'm looking at one of them specifically in mind, and that bow started, and all of a sudden on the northern side of the bow, you have your line normal shear would be increasing drastically in a relatively short time period.
Yes, exactly. Yes, absolutely. So if we can think back to our shear vector, and I do have it down here, just assume that it's from the southwest for simplicity's sake. But right here, this part, all of a sudden you are very normal to that particular part of the line. Is that what you were referring to, or am I missing the boat?
Yeah, that's exactly it. And I'm wondering if like you could not have the other ingredients there, and you could be looking at this storm and say, oh man, we don't have ingredients 1 or 2, and then all of a sudden you get your rear inflow jet surging in, and you're like, oh my God, now all of a sudden we do have all 3.
Yes, that's absolutely the case. And a lot of the times with the QLCSs, it doesn't happen right away. Like you need, maybe you need that rear inflow jet to make more of a cold pool so that you can balance it with the environment. I'm not sure. I think we have this team looked at research that is close to a decade old, and I think there's a lot of new opportunities out there to try to figure out what's going on. So great observation, Ian. Thanks for the question.
Yeah, thank you.
Are there any other questions out there? If not, I have one. So Jacob, is the 3 ingredients method, is it operationally being used right now, or is it still in development by the NWS?
Yeah, we have unrolled the training 2 years ago, and then the second half was delivered this year, and it is being put in practice. This was a Central Region initiative, just because we have some challenging storms up here. But now other offices are seeing it, and if I can, seeing how it is a great example of research to operations. I mean, you're taking peer-reviewed literature from academia, and then applying it to real-world operational meteorology, which is what I'm in. And so I love it, and it's starting to get used, I guess, to summarize your question. So, yes, sir.
Any last minute questions out there? All right, so it doesn't seem like anyone else has a question right now. So could everyone give a round of applause? Thanks for coming today.
Yeah, thank you so much, Jake. This was really great. Fantastic work.
Thank you. Appreciate it. Proud to be a Wisconsin alum. And so hello to all former faculty and new students. You guys are in the best university in the country. So thanks again for the invite.
Thank you, Jake. That's how we feel about you when you come out and do something like this.
All right.
Yeah, great to talk, Jacob. Thanks.
All right. I guess I'll sign off then, okay, Pete?
Yep, I'll stop the recording.